Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to today's webinar, Surface Drainage in Public Spaces and Building Thresholds. My name is Amanda and I'll be your host for today. In keeping with our custom, Engineers Australia acknowledges the traditional custodians of the countries throughout Australia and recognises their continuing connection to land, water, skies and community. We recognise Aboriginal and Torres Strait Islander peoples as the oldest continuous cultures on Earth and our first engineers. We pay our respects to them, their cultures, and to elders past and present. Before we get started, I'd like to acknowledge that today's event is being hosted with Engineers Australia's industry partner, ACO. ACO is a global leader in water management with products to collect, clean, hold and reuse water, addressing all phases of the water cycle and supporting water-sensitive urban design. ACO offers a range of products for drainage and other services both outside and within the building envelope. ACO in Australia was established in 1993 and is Australasia's leading manufacturer of water and cable management products, with production facilities located in Western Sydney, New South Wales. We thank ACO for their continued support. Today, we will hear from two speakers, followed by our live audience Q&A, which will be joined with another speaker, and I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Anthony Healy. Anthony is a chartered professional engineer and director at Eclipse, bringing more than 10 years of experience in civil and structural engineering. A UNSW graduate with a particular interest in stormwater design, he is passionate about delivering high-quality, efficient and practical solutions. Anthony is a proud husband and father of two beautiful daughters. He enjoys family time, hiking and using 3D printing to solve everyday problems. Please welcome Anthony Healy.
Good afternoon and welcome. I'm Anthony Healy, Director and Senior Civil and Structural Engineer at Eclipse Consulting Engineers. Today's session is part of Engineers Australia's Industry Partner Series, which is produced in partnership with ACO. Over the next 20 minutes, I'll be covering two simultaneous revisions that directly affect engineers working at building thresholds and in public spaces, and what they mean for best practice drainage design. Let's get into it. I want to start by framing the central problem, because it's often misunderstood in practice. The building threshold, the point where a building meets the external pavement, is not a single discipline problem. It's a coordination interface between at least 5 distinct design requirements. They are drainage performance, accessible design, slip resistance, waterproofing, and membrane continuity, as well as maintenance access. None of these can be resolved in isolation. If you design an accessible entry without thinking about drainage, you create a flood risk. If you design drainage without thinking about accessibility, you create a trip hazard. NCC 2025's broader Part F1 framing reflects exactly this reality. Water management now captures the full interface, not just the drain downstream. So why does this matter now specifically? Because both the NCC and the primary stormwater drainage standard have been revised simultaneously, and both in ways that directly affect threshold and public space design. On the building code side, NCC 2025 consolidates what were previously 2 separate parts. Part F1 covering surface water and Part F3 covering subsurface water. It's now in a single unified water management framework. This explicitly brings balconies, podiums, concrete roofs, attached awnings, and layered build-ups into scope more clearly than the current 2022 edition. On the standard side, AS/NZS 3500.3 2025 has made Appendix F normative. As a result, overflow at eaves gutters is no longer advisory, it is now a binding design requirement with an explicit calculation pathway. These two changes together mean that treating overflow and threshold drainage as secondary details is no longer compatible with NCC compliance for Class 2 to 9 building works. Let me walk through the framework changes in a little bit more detail. In NCC 2022, the two frameworks sat separately. For Class 2 to 9 buildings, stormwater was handled under Volume 1, Part F1, with a relatively narrow scope centred on roofs and downpipes. Subsurface water sat in a separate Part F3. For Classes 1 and 10, detached houses, garages and carports, drainage sat under Volume 2, Part H2. NCC 2025 makes structural changes to the Class 2 to 9 framework. So Part F1 now consolidates surface and subsurface water management. The scope explicitly expands to cover balconies, podiums, etc. The deemed to satisfy pathway for these Class 2 to 9 buildings remains AS/NZS 3500.3, but it now references the 2025 edition, which includes normative Appendix F. For Classes 1 and 10, the structure stays under Part H2, but the broader Part F1 scope does affect mixed use and podium projects. The practical shift is that drainage is less about a narrow roof plumbing mindset and more about managing the whole water path, which includes the hidden layers that can fail even when the visible drain lines are correct. A practical note before we go a little bit further. The final version of NCC 2025 was released on the 1st of May, but commencement dates vary significantly by state and territory. As can be seen in this table, the rollout is staggered across the country and likely won't be finalised until this time next year. The bottom line is always check jurisdiction commencement before treating the NCC 2025 as live law on a specific project. Transitional arrangements also apply in some states. That said, it is worth designing to the 2025 framework now, particularly for overflow design, where it provides clearer DTS support than the previous edition. Let me now get into the update applying to the standard, specifically the three changes in AS/NZS 3500.3 that have the most direct impact on designers working at thresholds and in public spaces. These three changes relate to overflow design, valley gutter design, and appliance connections, and they apply whether you're working on a simple residential threshold or a complex commercial podium. The first and most significant change, Appendix F has moved from informative to normative. In the 2021 edition, Appendix F contained guidance on overflow at eaves gutters, but it was advisory. In 2025, it is normative. Overflow pathways must now be designed with a calculation. Engineers must select a device type and verify its capacity against the required overflow rate. There is no longer a default assumption that an overflow detail is adequate without any supporting calculations. The second change concerns valley gutter design. Previously, the standard used a blanket 20 square metre catchment assumption for all valley configurations, which was a bit of a blunt instrument for larger or more complex roof geometries. The 2025 edition adds figure 3.6.2, which is a graphical method. It allows valley gutter design to respond to actual catchment sizes and rainfall intensity. The third change is the new clause 5.3.8, which adds explicit requirements for the connection of miscellaneous appliances to the stormwater system, including HVAC, condensate, pool overflow, and similar. I'll walk through the Appendix F overflow design and sequence because this is where the practical design work happens under the new normative requirements. The sequence has three main steps. Step 1, calculate the required overflow rate, which is denoted Q star. This is determined from the catchment area up to 400 square metres in size and the design rainfall intensity for the site at the selected AEP. Step 2, verify that your selected device's actual overflow capacity Q is greater than or equal to Q star. If it is not, resize or change device type. Step 3, device selection. The standard now provides actual capacity data for 3 device types. F4.2 covers back gaps, F4.3 covers slotted gutters, and F4.4 covers front bead overflow. The standard notes that in F4.5 that computational methods and CFD are signposted as a future direction, but are not explicitly included in this version of the standard. The key implication for designers. Overflow is now a designed system. You need to calculate, select, and verify. With the regulatory and standard updates in place, let me now turn to best practice design, specifically how we apply this framework to real decisions at thresholds and in public spaces. This is where the code knowledge meets detailing practice. The threshold is where 5 distinct design requirements converge, and none of them can be resolved independently. Drainage performance. The primary drainage path must handle the design flow. The overflow path must be designed, and both must still work under partial blockage. Accessible design. The approach and threshold must comply with accessibility requirements. For classes 1A and class 2 sole occupancy units, that now reflects the Livable Housing Design Guidelines Silver Standard. Step-free entry doesn't mean flat, it means the accessible route is preserved. Slip resistance. The surface must meet the relevant AS 4586 classification for the wet condition, not just dry. Waterproofing and membrane continuity. The drainage detail and waterproofing plane must be coordinated as a single system. A drain not integrated with the membrane upturns is a leak waiting to happen. And maintenance access. The threshold must be inspectable, cleanable, and repairable without dismantling the full assembly. NCC 2025's broader Part F1 framing reflects this integrated requirement. Let's look at the general design method for surface water drainage sizing under clause 5.4, which is a 5-step process. Step 1, select the appropriate AEP. Under table 5.4.3, this is consequence-based. Where impeded access to hospitals or institutional buildings is a risk, you need a higher AEP. Step 2, determine rainfall intensity using Appendix D and clause 5.4.5. Use a 5-minute duration, and the intensity must be site-specific from BOM IFD data. Step 3, calculate runoff using equation 5.4.8. Key runoff coefficients, 1.0 for roofed surfaces, 0.85 to 0.9 for impervious paved surfaces, 0.8 for sealed joints, 0.6 for open joints. Step 4, size the primary drainage using Manning's equation or open channel methods with blockage factors applied, 0.5 for sag pits and 0.8 for on-grade pits. Minimum pipe sizes are diameter 90 for residential and diameter 150 downstream of pits. Step 5, which is now an explicit design requirement, design the overflow using Appendix F for eaves gutters. Surcharge outlets under clause 5.4.12. Exit velocity must not exceed 0.15 meters per second through a graded outlet, which must be located clear of buildings and within the property boundary. An important note, the nominal method under clause 5.5 and Appendix K is for single dwelling urban lots under 1,000 square meters only. It's not applicable to public realm or commercial threshold projects. One of the most important principles in threshold and public space drainage design is to design for blockages, not just peak flow under clean conditions. The numbers on this slide come directly from AS/NZS 3500.3 and the City of Sydney's public domain criteria, noting that the City of Sydney has substantially higher requirements than most local governments, and it can often be held as the gold standard for public space drainage. Clause 5.4.10.1 specifies blockage factors of 0.5 for sag pits and 0.8 for on-grade pits. That means that your sag pit is designed for 50% of its clean capacity, assuming the pit will be half blocked at the design event. The City of Sydney's public domain specifications go a step further, applying 95% blockage to strip drains, effectively sizing for near zero flow. On overland flow, the 1% AEP limits for pedestrian and shared zones are as follows. Maximum ponding depth, 50 mils, maximum flow width, 1.5 metres, and maximum depth times velocity product, 0.4 metres squared per second. The drains must not be the only line of defence. The surrounding falls, overflow routes, and adjacent surfaces must work even when the inlet is completely blocked. Putting this together at the threshold detail level, there are 6 design moves that work well and a handful of failure modes that are the most common. Good design moves include a recessed door slab or a local set down, which creates a drainage recess without introducing a step on the accessible route, and a linear slop drain immediately outside the opening, intercepting surface runoff, with positive falls directed away from the opening wherever possible. Sill pans and membrane upturns detail continuity, which allows the waterproofing plane and drainage detail coordinated as a single system. A designed overflow path if the drain is blocked, and new in the 2025 code, clause 5.3.8 requires HVAC, condensate, and pool appliances to be connected via a tundish with a 25 mil air gap. The failure modes that I see most often in practice: reverse falls after paving settlement or construction finish changes, drains sized for clean grate peak flow with no blockage factors applied, and the threshold drain being the only line of defence with no overflow path. Lastly, level entries converted to trip hazard by construction tolerances. Slip resistance is closely linked to drainage performance, and I want to be very direct about one thing. Slip resistance is not separate from drainage. A surface that stays wet, ponds, or accumulates dirt and algae becomes a slip risk, even if the nominal material rating was acceptable at handover. The NCC calls up AS 4586 for pedestrian surface slip resistance classifications. There are 2 primary test types. The wet pendulum test can be conducted in situ or in a lab and gives P0 through P5 ratings. P4 and P5 are required for external wet pedestrian areas, ramps, and pool surrounds under the NCC deemed to satisfy pathway. The oil wet inclining platform test is lab only and gives R9 through R13 ratings, which are used for contamination prone areas. For external public realm and threshold applications, the wet pendulum is your primary reference. The real risk here is the material that fails its test, but it's also the material that passes the test dry and then fails in practice when wet, dirty, or affected by algae. Designed for the wet condition, not the dry showroom condition. The final design principle, and the one that is most often deferred until after handover, is maintenance. NCC 2025 signals this directly. Surcharge outlets must be visible and noticeable to building occupants under clause 5.4.12. Exit velocity through a graded surcharge outlet must be 0.15 metres per second or less, and the outlet must be clear of buildings and wholly within the property boundary. For threshold drains, the design must include provision for inspection and cleaning. That means removable grates, clean out points at drain heads, and enough freeboard tolerance so that minor silt accumulation does not immediately cause ponding at the building entry. The sizing must apply blockage factors, not just peak clean flow capacity. And as-built verification before handover is essential. If threshold levels, fall directions, and drain positions have shifted during construction, which happens more often than you might think, those changes need to be caught and corrected before occupation. 5 quick takeaways to finish today's presentation. First of all, NCC 2025 makes water management broader. Even though Part F3 has been removed, Part F1 now captures surface and subsurface drainage design together. Check your jurisdiction's adoption date before treating it as live law on any project. And secondly, Appendix F of AS 3500.3 is now normative. overflow at eaves gutters must be designed with a supporting calculation. 3 device pathways, back gap, slotted gutter, front bead, each having a specific capacity method as laid out in the standard. Thirdly, valley gutter design gains flexibility, and the new clause 5.3.8 adds explicit requirement for HVAC, pool and appliance connections to the stormwater system. Fourth, apply blockage factors in surface water design. Sag pit factor is 0.5. Design the surrounding falls and overflow routes, not just the inlet. Fifth, the threshold is a coordination problem. Drainage, accessibility, slip resistance, waterproofing, and maintenance must be resolved together, not in separate discipline silos. That brings me to the end of today's content. Thank you very much for your time. I'm happy to take questions for the live Q&A at the end, and if you'd like to continue the conversation after today, my contact details are on the screen. A final thank you to Engineers Australia and ACO for the opportunity to speak with you today.
Thank you, Anthony, for your presentation. I'd now like to welcome our second speaker, Rochelle Ramage. Rochelle is a specification representative with over a decade of experience in drainage design, surface water management, and technical product support across commercial, residential, and public realm projects. She works closely with engineers, architects, and contractors to optimize trench drainage performance, ensure compliance, and support constructible design outcomes. Rochelle delivers regular CPD sessions, providing clear, practical guidance on hydraulic behaviour, product selection, and installation considerations. Her work centres on helping engineering teams achieve safe, efficient, and resilient drainage solutions through evidence-based specification. Please welcome Rochelle Ramage.
Good afternoon, everyone. I'm Rochelle Ramage, one of ACO's specification representatives here in Melbourne. It's great to be with you, and a big thank you to Engineers Australia for hosting today's session, and to Anthony Healy for his presentation earlier. Today, we're going to look at surface drainage in urban environments, from large public spaces right through to the threshold of a building. This is an area that often gets overlooked in design, but when it fails, it becomes very visible very quickly. Today, my goal is to show you how to get it right. Surface water management is ultimately about protecting people, property, and the public realm. When runoff isn't controlled properly, it leads to damage, disruption, safety hazards, and environmental impacts. Good drainage prevents all of that, and it starts at the surface. Here's what I hope you take away from today. Designers who get the walking surface right, in both wet and dry conditions, think about pavements as a system. Flat, drainable surfaces, grates that support safe mobility, channels that actually move water, and materials that last the design life of the project. We'll look at two key applications, public urban spaces and building entrances. They behave differently, but the design principles are the same. As pavements meet the building line, the design challenges change. Entrances need to be accessible, safe, and compliant, and they need to manage wind-driven rain without compromising the door system or the waterproofing. This is where surface drainage becomes highly specialised. Public urban spaces are complex environments. They carry huge volumes of foot traffic, sometimes vehicles, and they need to stay safe and usable in all weather. These pavements weave through cityscapes, connect to buildings, and often become the accessible thresholds people rely on every day. When we move from public pavements to building entrances, the design becomes much more specialised. Here, we're not just dealing with the general runoff, we're dealing with accessibility, waterproofing, door systems, and wind-driven rain. And this is where threshold drainage comes into play. It's an area where small mistakes can lead to big failures. Threshold drainage starts with two things, design and certification, and understanding the pavements and door system around the entrance. The door type, the slab depth, the membrane detail, all of these influence the drainage solution. Once you understand those constraints, the rest of the detailing becomes much clearer. Stormwater needs to be managed at building entrances, which is why civil engineers are now getting more involved in this area of design. To ensure barrier-free accessibility, level entry thresholds have become a necessary design feature at building entrances. These modern types of level thresholds were developed as an alternative to the conventional threshold set-downs. Originally, level thresholds were driven by the access and mobility requirements under AS 1428, and then reinforced through the Livable Housing Design Guide. With NCC 2022, there's now increased focus on level entry thresholds across both commercial and residential buildings. Linear drains are incredibly versatile and are installed at the building entrance to capture wind-driven rain. The key is understanding how they fit into the compliance pathway and the design requirements of that application. One of the biggest issues we still see is a lack of general clarity around the compliance pathway. Designers often ask whether a level threshold detail is considered deemed to satisfy or whether it triggers what is known as a performance solution. To differentiate the two, deemed to satisfy is a prescriptive approach. It lists exact materials, dimensions, and construction methods. The performance solution is a tailored solution that achieves the same result with the project objectives in mind. The certifier makes the call as to which pathway to choose, regardless of which the design requirements are exactly the same. So the correct approach is to design to the higher standard from the start. That way, whichever pathway the certifier chooses, the design and documentation already supports it. Waterproofing is one of the most critical parts of threshold design. AS 4654.2 sets the vertical upward termination height of the membrane, often called the required step down. This height isn't arbitrary, it's based on the wind class for the site. So the step down becomes the recess that must accommodate the membrane, the drain, and the door track. If the recess isn't deep enough, the detail simply won't work. NCC 2022 provides clear, deemed to satisfy requirements for waterproofing, so confirming the wind class early is essential. The National Construction Code provides comprehensive deemed to satisfy, or DTS, provisions for waterproofing across both Volume 1 and Volume 2. The DTS provisions establish exactly which elements must be waterproof, so impervious to moisture, and which must be water resistant, capable of resisting moisture without damage. The practical takeaway is simple. Confirm the site wind class early, apply the correct membrane termination height, and coordinate that height with the drain recess and the door track profile, so the detail is constructible and compliant. One common way to achieve a level threshold is to use pedestal or pod pavers to raise the external pavement level. This provides a visually continuous pavement to the building entrance. It also hides a subsurface drainage element beneath the pavers. Hiding drains, whilst aesthetically pleasing, can give rise to all sorts of access and maintenance problems. The purpose of this drain is to remove water from the pavement, not to remove wind-driven rain at the doorway. On exposed terraces and balconies, pedestal pavers can be susceptible to wind uplift, and this risk must be mitigated, and the client must be made aware of this. A separate threshold drain at the building line is used to remove wind-driven rain that effectively hits the door and drops down to the drain. Level thresholds are inherently susceptible to failure if they're not detailed correctly. There's a few non-negotiables. The external area must slope away from the building. That external area must have its own primary drainage element. The threshold drain must sit adjacent to, but external to, the building line. And importantly, the threshold drain is designed to capture wind-driven rain only. It is not the primary drainage system. Depth is one of the biggest constraints near a building. Shallow slab construction is becoming more common, and topping screeds or slabs can vary significantly. We're often working with drainage depths of less than 30 mm, so the drainage solution must be purpose-designed for shallow applications. And this is where stainless steel threshold drains and shallow profile channels become essential. Now let's focus on the threshold drain itself. No two projects are the same, and the threshold drain needs to cater to the door type, the slab depth, and the waterproofing detail. Sometimes a conventional linear drain is fine. Other times you're going to need a purpose-designed threshold drain that interfaces directly with the door track. key considerations will include how the door integrates with the drainage element, whether the sill is drainable, and whether the drain can actually handle the expected flow. Remembering, this is wind-driven rain, not catchment or roof runoff. Once you answer those questions, the right product becomes obvious. Door type is one of the biggest determinants of which drainage system is appropriate. Sliding doors, bifold doors, and some floor-to-ceiling windows with recessed mullions require an integrated linear drain that interfaces with the door track. This is because we need to capture water through the weep holes and the track itself. On the other hand, hinge doors, garage doors, commercial sliders, and top-mount bifolds only require a detached linear drain. These door types don't need a subsill interface. The drain's job is simply to prevent runoff. Regardless of where the water comes from, pavements, wind-driven rain, or incidental splash, the drain has one job: to intercept and evacuate stormwater safely. To size a drain correctly, we need to understand the fundamentals of hydraulic performance. We're going to look at things like the shape of the channel, its slope, and its length. Hydraulic performance is essentially the amount of water a drain can collect and discharge over time. If the drain is undersized, it's going to flood. If it's oversized, you're going to add unnecessary cost to a project. Many designers use simple pipe or open channel theory, but that assumes uniform flow, meaning the water depth and velocity are constant along the channel, and that's not how trench drains behave. Trench drains operate under non-uniform flow because water is constantly entering along the length of the channel. The water profile changes as it moves downstream. Manufacturers should provide hydraulic performance data that reflects this, ideally based on real testing or modelling. Non-uniform flow is a more accurate way to model trench drainage. It accounts for the water already inside the channel, plus the continuous addition of water entering through the grate. This is why trench drain hydraulics can't be treated like a pipe. The water depth increases along the run, and the velocity changes with it. Understanding this helps you size channels correctly and avoid failures. The shape of the channel has a huge impact on hydraulic performance. V-shaped channels create deeper water levels, which increase velocity and help move silt during low flow events. This is especially effective when the channel material has a low coefficient of friction. U-shaped channels are common, but they don't self-clean as effectively in minor storm events. This is the same principle behind egg-shaped sewers. Deeper flow paths improve performance and reduce blockages. When we talk about hydraulic performance, the slope and the length of the channel run play a major role in how effectively a trench drain moves water. A sloping invert increases the velocity of water inside the channel, which means it evacuates faster and increases the overall capacity of the system. Wherever possible, we want to work with the natural topography of the catchment, but in flat pavements, that's not always available. In those situations, a trench drain with built-in falls becomes the only reliable way to achieve positive drainage. Run length also matters. The shorter the distance to the outlet, the more capacity the channel has. This is the characteristic of non-uniform flow. As water enters along the run, the depth and velocity change, so shorter runs perform better. If you look at the three options on the slide, options B and C will always handle larger catchment areas than option A, simply because they reduce the run length to the outlet. It's a simple design decision that can dramatically improve performance. Beyond the pure grate intake area, which is the open area of the grate, there are other factors that influence grate hydraulics, including the slot size and the orientation. The grate is the first point of entry for water, so its intake capacity is just as important as the channel beneath it. Slot size, slot orientation, open area, and even the grate material all influence how effectively water enters the system. The number of slots and the raised slip-resistant nodules also impact the flow of water and tend to retard the flow and help direct the water into the slots. For threshold drains, we're dealing with wind-driven rain, not catchment runoff. That means the grate doesn't need to handle large volumes, but it does need to capture water consistently along the entire length of the doorway. The water blown up against the doors from the wind is the main runoff a threshold drain needs to deal with. Specifically, this is the water that collects on the vertical surface, so the surface of the door. Threshold drains are sized to capture wind-driven rain and wash down only. The hydraulic design of the drain is based on a severe storm event for various wind zones for different regions of Australia. The door dimensions need to be considered, and this is factored down by the roof design, which may produce partial cover. The hydraulic capacity of the drain is usually limited by the outlets. The more and the bigger the outlets, the better the system's going to work. And as you can see in the drawing at the bottom of the slide, shortening the length of a run by adding outlets also increases the channel capacity too. Ideally, drainage elements should endure for the life of the pavement. Premature replacement of drains makes asset management expensive and works against the principle of sustainability. There are 4 elements to consider: the strength of products under live loads, the durability of materials during their life exposed to a particular climate, and how the drainage systems are tied to doors, slabs, and pavements, as well as the ease of maintenance. AS 3996 classifies load classes for pedestrians, so Class A, all the way up to aircraft pavements, Class G. This standard generally applies to grates only. The only standard written specifically for grated trench bodies and grates is the internationally recognised EN 1433. This standard includes different grate widths and different channel sizes. It specifies test methods with loads up to 900 kilonewton for both the grate and channel body. The test accounts for both serviceability and ultimate loading. It's an important standard, particularly where vehicles are involved. Public urban spaces and the space outside of buildings tend to fall into the load class C and D if they're accessible to vehicles, or class A or B if vehicles are restricted or prohibited. In most cases in commercial applications, there's always going to be the need for service or emergency vehicles. Trench drain bodies are generally made from various materials, which could be concrete, polymer concrete, GRC, plastic, or stainless steel. For durability, a trench drain must be strong to withstand the imposed loads, smooth enough to allow for efficient flow, and resistant to the local environment and contaminants. Selecting the correct material for the application is critical to avoid premature failure. Grates, slotted tops, and channel rails are the wearing surfaces of trench drains. They are also the most visual elements. Iron is by far the strongest material, but it's not as corrosion resistant as a composite material. Rails need to be integrally cast, not just mechanically fastened to the channel. Selecting the correct material for the application is critical to avoid not only premature failure, but deteriorating aesthetics through corrosion and wear. Drainage channels need to be encased in cement concrete to ensure they are structurally part of the pavement. The encasement needs to be designed for the project and needs to take into effect construction and design loads, ground conditions, and pavement types. Also, steel reinforcement may be required at times. For some door types, threshold drains will have direct interface with the door elements. There are 2 types of designs. Type 1 is where the drain has a provision to accommodate the subsill of the door system. This is used for door sills that have a subsill. Type 2 is where the entire door track is positioned into a purpose-designed tray which forms part of the drain. This is shown in the installation drawing. This type of threshold drain can accommodate doors with sills only, or with a sill and subsill. To avoid galvanic corrosion, nylon pins are used to stop the aluminium track and stainless drain from making contact. Installation sequencing is critical. Threshold drains sit above and separate to the waterproofing membrane. The typical sequence is to create an oversized recess, waterproof the recess, set the drain on levelers, install the door system, and grout around the recess with high-strength, non-shrink grout. If the drain needs to interface with the door track, it must be installed before the door system. Drainage channels can also be installed on a radius, and you can do this either by opening up a gap on the inside or outside edge of the channel for a large radius, or by grinding the channel units for a tight radius. If drains are hard to maintain or grates rattle loose, their lives will be shortened. If grates aren't locked into the channel, they can damage the channel under load. Loose grates, particularly in trafficable areas, can be very dangerous. A boltless locking system on grates is quick and easy to maintain for cleaning. The other option is to have bolted grates, but it comes with the risk of the grates vibrating loose over time. And it's common to see that once the bolts are removed during maintenance, they aren't put back in place, causing a safety risk for users. Slot drains require discrete access points that help the designer preserve the visual continuity of the pavement, but they do need access points to be installed at the start and end of every run, or every 20 metres or so throughout. We're now going to look at the design principles and legislative requirements of managing runoff. Much of this is designed around ensuring walkability and accessibility. Flat pavements offer better usability, better accessibility, and better outcomes for pedestrians and vehicles. Linear drains support this by collecting water along the surface, rather than relying on complex falls into isolated pits. They interact directly with shoes, wheels, canes, and tyres, so they need to be designed with people in mind. When drainage isn't considered early, contractors are forced to create complicated falls to push water into pits. That requires precision grading, and even then, pavements settle over time. The result is water that doesn't go where it's meant to. It can pond, it creates a hazard, and it reduces usability. Uneven pavements also create accessibility issues, especially for people with mobility challenges. A simple linear drain allows for a single, consistent fall across the pavement. You can even introduce internal slopes within the channel to move water more efficiently. This reduces pipework, it reduces maintenance, and it improves the long-term performance. There are two main types of linear drains: precast modular systems, which offer consistent quality and fast installation, and cast in situ trench drains, which rely heavily on workmanship and are harder to clean and maintain. Cost is always going to be a factor, and this independent study by Ryder Levitt Bucknell compared 3 drainage approaches in a Sydney car park. The precast modular trench drain came out more than 10% cheaper than point drainage with pits, even when you include all the materials and labour. The takeaway is really simple. When drainage is considered early, the design becomes more efficient, more cost-effective, and more reliable. Heel safety is one of the most common concerns we hear from designers and asset owners, but there's no Australian standard that sets a heel-safe slot size. So we go off the international guidance, which is usually around 8 mil. In practice, there's a balance to strike. If the slot is too small, it won't collect enough water. And that's why most designers settle on a 10 mil as a sweet spot. It's safe for heels, but it's also hydraulically effective. AS 1428.1 was updated in 2021, and it now gives very clear direction on how slots and openings must be orientated. Slots between 8 to 13 mil must run across the dominant direction of travel. This will prevent wheels, canes, and mobility aids from tracking into the openings. If the slots are under 8 mil, orientation becomes optional. But for most public pavements, we're working in that 8 to 13 mil range. So this is why great selection and orientation is so important at building entrances and in public spaces. Bicycle safety is covered under AS 3996, and this standard looks at the type of bar elements used in a grate and the maximum slot dimensions to prevent tyres from getting wedged. It's a critical consideration to shared zones, cycle paths, and anywhere bikes and pedestrians mix. Slip resistance is becoming a major focus for asset owners, and for very good reason. If a grade is too smooth compared to the stunning pavement, people are going to slip. And if it's too rough, they're going to trip. So the grate needs to match the slip characteristics of the pavement around it. AS 4586 sets out the slip resistant classifications, and HB 198 helps you choose the right rating for the environment. For example, oily wet areas use the R rating, wet barefoot areas use A to C, and most external pavements rely on the P rating. Manufacturers should always provide NATA-endorsed test certificates so you know exactly what you're specifying. This table from HB 198 shows the minimum slip-resistant requirements for different environments. For external pavements, you'll typically be looking at a P4 or P5, depending on the slope and the level of exposure. The key point is that the grate must meet the same slip-resistant expectations as the pavement, otherwise the surface becomes inconsistent and unsafe. Now a little bit about ACO. We're a global manufacturer specialising in water management. In Australia, our focus is on supporting engineers, architects, contractors with technically robust drainage solutions that meet compliance, performance, and design life expectations. Worldwide, our core business is water management, with the manufacture and supply of products to various industries. Hydraulic performance, compliance with standards, material durability, installation guidance, all of that technical support comes with the system. Our role is to help you design drainage that performs reliably for the life of the asset, no matter the environment. When water lands on the surface, ACO has products that collect, clean, hold and recycle or release water in a sustainable manner back into the water cycle. Worldwide, ACO supply water management products to control both the quality and quantity of water. ACO in Australia is a member of the ACO Global Group of companies manufacturing on all major continents. The ACO Group is an 80-year-old family-owned organisation and was established in Australia over 30 years ago. Our manufacturing plants are based on the East Coast and our head office is in Western Sydney. We are NATA and ISO 9001 accredited. We have sales offices and warehouse in every major city. Last year, we officially acquired the Helgen Trade Waste business and brand name. Across our two companies in Australia, we manufacture products for the civil engineering and commercial plumbing sectors. These are products that are designed to be installed inside and outside the building envelope. We sell different product lines, but specialising commercial trench drains for light to heavy duty applications, cable pits and access covers in all material types and sizes, as well as underground stormwater tanks. When describing the need for sustainable solutions, environmental impact and durability are topics that must be discussed together. On the main, these products are in highly trafficked commercial areas and require to be securely integrated into the pavements. They are manufactured to be mechanically strong, have thermal and corrosion resilience, and to be UV stable. These materials' attributes are important as products need to last the design life of the project without having to be prematurely replaced or discarded. Iron, polymer concrete, as well as stainless steel are amongst the types of materials that are needed for durability. And on the main, these materials at the end of their design life are safe, they can be used for recycling, or they can be resold. Being an Australian manufacturer, the sourcing of our local materials through the manufacture of local products ensures transport distances to site are short compared to the excessive carbon footprint associated with companies choosing to import by sea or air. As part of this, we have in 2023 commissioned a report that identifies our environmental impact across our supply chain. This will form the benchmark against which we evaluate and monitor our progress in the coming years. We are currently undertaking a comprehensive life cycle assessment, an LCA, of our core products to inform future product design and sourcing to ensure a further reduction of environmental impacts and to support the development of 2 Environmental Product Declarations, or EPDs, scheduled for release in Q3 2026. Beyond our products, we also have a lot of support for engineers, both with online DIY channel and grate sizing programs, and tailored product support by our technical services engineering team. These DIY programs are a fantastic way to get quick information on hydraulic performance of channels and of grates. Hydrolite is our channel sizing program, and GIC is the grate intake calculator, and both of these have been grounded in experimental test data. We also have another program called Scheduler, which can draw trench drain runs and provide layouts, long sections, and a bill of materials to assist in procuring and installing the products, which is particularly helpful when you're specifying sloping runs. Ask ACO is a corporate initiative designed around advice and industry education. Services are offered free of charge and obligation and are designed to complement, not substitute, professional engineering advice. In partnerships with Engineer Australia, we've released 2 white papers relating to trench hydraulics and best practice for stormwater design in public spaces. These are available for download on our website. And lastly, I wanted to introduce you to our dedicated sales team around Australia. I look after Victoria and Tasmania, Kate is based in New South Wales, Gary in Queensland, Andrew looks after South Australia and the Northern Territory, and Maria is based in Western Australia. So please do get in touch with your local rep. We'd be delighted to meet with you and chat trench drains even more. We will follow up with a post-event email with some useful resources for engineers that will help make specifying drainage easier. Thank you for your time, and now it's over to Amanda.
Thank you, Rochelle. And I'd now like to welcome Darren Chan, who is joining today's Q&A session. Darren is the brand manager at Echo for civil construction products and the NATO authorised representative for Echo's testing laboratory. Echo continues to support engineers and designers with innovative products and free online design tools. And today we are running a competition. And to enter, please scan the QR code on screen or use the link in the description box below to answer the following question. If a certifier indicates that a level entry threshold to a large restaurant may require a performance solution instead of a deemed to satisfy approach, how would you approach your design? To understand your thoughts, we've set up a short poll before the Q&A. So if you can, please scan the QR code on screen or follow the link in the description box below. The results will be displayed on screen. Thank you. So we'll kick off. We just have a few questions. And the first one is, what has been the scope of your involvement so far with drainage along buildings? For some projects, it's in our scope. I've been involved in discussions with other designers. As yet, I've had no involvement. So if you'd like to vote now. And we'll just let those come in and invite Darren to comment on your answers. Thank you so much.
Yeah, good afternoon, everyone. Thank you for joining this webinar, and thank you for participating in this poll. So these poll questions will, for ACCO, it helps us understand your involvement in designing, and helps us, bring different products and technical support that you may require. So yeah, it looks like most people are involved in designing drainage and buildings, which is good. And yeah, please have a look at some of the ACCO products that we can provide and help you with your next project.
What is the most problematic design challenge you would foresee? 1, coordinating the membrane step down with slab depth. 2, integrating the drain with the door track. 3, managing wind-driven rain effectively. 3, ensuring the detail meets DTS or PS requirements. And 4, contractor installation and buildability. Thank you, and please vote. Darren, if you'd like to comment on the findings.
As a manufacturer, we like to understand what your challenges are when you're designing level threshold drainage. This helps us provide education, I suppose, to educate the design community and the engineering community, so we can build presentations and look at topics that, I suppose, that from this poll that are most problematic in your design, and then help you, I suppose, integrate a good specification that meets all the compliance requirements into your project.
Thank you, Darren. And just winding up this poll, our final question is, what do you value from a drainage supplier? Just get that on screen. Downloadable drawings, data sheets, hydraulic sizing, drainage integration advice, drain, run drawing, run schedule and services, phone face-to-face assistance. Thank you. Darren.
At ACCO, we pride ourselves on our technical support, and Rochelle touched on what we can provide in her presentation. And we like to continue offering services and material that can help you specify drainage products, ACCO products into your projects. So it's good to understand what's your requirement, what you most want from us. And definitely, we've got a lot of downloadable drawings and data sheets that you can download from our website. We have a technical support team here that can help hydraulic sizing, and even if you need to size up channels, you can easily get on to one of our DIY programs that we offer on our website. We would love you to have a look at our technical support, and we always want to build on what we have already. So thank you for everyone for participating in the poll.
Thank you, Darren. And thank you, everybody who participated in that poll. It's just a live way of getting an understanding of your thoughts. And we'll now move into our Q&A. And just a reminder to please ask our speakers your questions via the YouTube chat box, and let me know who your question is directed to. Big thank you, as always, to everyone who submitted questions whilst registering for today's webinar. And I might kick off with some of those, starting with you, Rochelle. Rochelle, we've had a question that came in from Mohammed, who is watching in somewhere in the Middle East. Good afternoon to you, whatever time it is there. Asking you, Rochelle, what are the best practices for coordinated finished floor levels, FFL, with external grading and drainage layouts? Thank you, Rochelle.
Thanks, Amanda. So the main thing is coordinating the FFL early. So coordinating across the structure, waterproofing, with architecture and hydraulics, just to ensure that it's compliant and that the compliant separation is made from the membrane termination heights. We also need to think about external surfaces falling towards the main drainage element, so never towards the threshold itself, with stormwater outlets located at the lowest point of the graded plane. We need to align slab set downs, screed thickness, door track heights, as well as recess depths as well. So threshold drains sit above the waterproofing membrane whilst meeting AS 1428.1 accessibility requirements. And I'll see if either of the other guys want to add anything on this.
Yeah, look, yes, best practices. I suppose you've got to coordinate with all the designers. Discuss this with your architects. Architects will design a certain, floor levels they want, and I suppose for an engineer, you just got to make sure you're tied in your pavement designs, your drainage design, all meet the requirements and meets the NCC and AS 3500. And just make sure, everything flows away from the building. That's probably the most critical thing. You don't want to make water come back to the building, which can cause issues from hazards to damage to the building.
Thank you for that, Darren and Rochelle. Darren, we have a question that's come in from Daniel. Daniel is watching this afternoon from Victoria. Good afternoon to you. Asking you, Darren, what is the maximum grade for a trench grate installed perpendicularly halfway through a sleep ramp 1 to 10, and at what point will it lose its effectiveness, where the runoff would just bypass the grate? Thank you, Daniel, for that question.
Yeah, thanks, Daniel. Good questions. Look, you can install trench grates across ramps. There's no issues with that. It's probably with the steeper the ramp, you don't want to install your trench grate flat with the grate flat. That means you'll be causing some trip hazards, I suppose, and it's sort of you're designing in a speed hump. So what you want to do is design the trench grate to follow the slope of the crossfall of the ramp, and then it's down to your contractors on site to using ACO drain on a precast channel. They will just have to set it up and support it so it doesn't move during the concrete pour, and ensure that it's flush across the ramp. So there is no really maximum steepness to it. I suppose the steeper it goes, the more fiddly, more attention to detail the installer has to have on site to make sure that it's installed correctly. In regards to losing the effectiveness of the runoff, now, look, ACO have done a lot of testing in regards to the grate intake. Rochelle touched on that in her presentation. So we at ACO, we've sent all our grates to the University of New South Wales Water Research Lab. We've had grates placed across a flume, which the flume could be put on a slope, increased slope from 0.5% to 9% slope. So at ACO, we've got data on the intake results of all our grates placed across the ramp. We understand it's a good question that you asked, the effectiveness. So what we learned from these tests was that, yes, slope does matter. The steeper the slope, I suppose the faster the velocity of the ramp, and then you'll get water tending to either, if it's a longitudinal grate that goes across the ramp, the bars, the faster the water flows, the water will hit the bars and they'll tend to splash up and cross the grate down to the downstream. Whereas the transverse grates with the bars that go across the grate, water will, as the water head builds up or the higher velocity, the water will tend to start trickling along the bars and will bypass. So we've learned a lot about our grates. If the steeper the slope, you probably want to go for a wider grate than a narrow grate. Probably the spacing of the grates will help on a ramp too. The wider the spacing, that means the water will build up velocity coming down. So you might want to put more wider grates, or you want to put narrow grates at shorter intervals. So look, we also learned that even the nodules, the anti-slip nodules on the bar help with intake too. Sometimes the nodules are raised. With these raised nodules, depending on the flow rate and the depth of flow, they hit these nodules and it redirects it into the grates. So look, you can be assured that if you're specifying an ACO grate, we've got test data that can back up the intake results. We can provide the intake on our great intake calculation sheets. This is all based on the test results. We can provide an output that will give you links that show you videos and photos of the actual test. And if you need a quick review of the grade that you've specified, you can get onto our DIY program that's on our website that you can check the grades. Otherwise, you can contact Mako and we can help you provide those results.
Thank you, Darren. Anthony, we have a question that's come in from Roshan, who is watching in Tasmania, asking you, Anthony, in practice, how do you balance compliance with AS 3500 and council stormwater requirements against site-specific constraints like minimal fall, accessibility, DDA compliant thresholds, and retrofitting drainage into existing public spaces? And what's the most common design or construction mistake you see at the building threshold public space interface? Great question, Roshan. Anthony.
Excellent. Thanks, Amanda, and thanks, Roshan, for your question. I think this question really gets to the heart of the issue, which is that design of the threshold is an issue where lots of disciplines come together. It's a multidisciplinary issue, and coordination can be quite difficult, particularly with projects where we're looking at retrofitting. So from a practical point of view, if you start with accessibility as being your hard flaw, it's something that you should design around, probably not against. It very clearly lays out what your minimum falls are to be, or I guess what your maximum falls are meant to be, which is 2.5%. That actually sort of gives you a very narrow window to work with. In practice, there's not really a minimum slope that that is specified by either the NCC or AS 3500. But in practice, if you're designing for anything less than 1%, 1 in 100, you are likely to end up with construction issues when it actually gets built. We see quite often that when you are specifying 1 in 200 or even 1 in 100, contractors are actually building things that are dead level, which could be a little bit of a problem. You end up with puddles right outside your doorways. So there are a couple of practical things you can do, particularly in a project where you need to retrofit. One of the solutions that Rochelle touched on was using pedestals for pavers, which actually allows for you to achieve your drainage underneath the dead flat finished surface. Other options that you have include screeding or building up a finished surface to actually achieve positive falls away from your threshold drains. So there are lots of practical options that you have, but in practice, when you're working in the retrofit space, you may end up looking at not a DTS solution, but a performance solution. It is a legitimate option in a lot of these cases. As far as most common construction mistakes you see, the first one is obviously around falls. No builder is going to be perfect in achieving the falls that have been designed by the engineer, and some tolerance has to be allowed for in the design. In the worst case, you often end up with, in isolated areas, falls towards the threshold, which is where these threshold drains really become critical in being installed. In a broader sort of stormwater scope, the most common mistake, not in construction, but actually after handover, is the lack of maintenance. It happens time and time again. It's not just threshold drains, it's to do with strip drains in drainage more generally, pits and pipes, all these sorts of things. The current version of the NCC is trying to make it a little bit easier for maintenance to occur, but it is so common to just walk out onto the street on a rainy day and see a pit or a strip drain that is flooded because it's been blocked. It's probably been years since it's been cleaned out, or the grates themselves aren't able to be removed because they're screwed down. It makes it quite difficult. And as a result, as a designer, one thing that you must consider is what actually happens to the stormwater when these drainage systems are blocked. Where does the water go? That's where the real flood issues are being seen in practice, is if you don't have an overland flow path that allows water to escape somewhere, particularly in these urban areas that are highly built up. you will see flooding issues. So I think those are two of the most common mistakes that I'm seeing in public spaces.
Thank you, Anthony, for that explanation to Roshan's question. We have a question that's come in live for both to Rochelle and Darren, asking if rainwater hits the wall, should that also be considered as part of the vertical catchment area under the relevant standards? Or is it not considered in threshold design? Rochelle, if you want to start off with that.
Yeah, I'll start off on it and then Darren can go into a little bit more of how we size them up through our technical services team. But in short, yes, the wall is counted as part of the vertical catchment area. But if the wall is partly sheltered, then that portion that's exposed to wind-driven rain is calculated. So there's a little bit of technicality involved in it. We do offer some sizing tools through our technical services team. So I'll let Darren go into a little bit more detail about that.
Yeah, definitely you've got to consider the wall, especially in high rises. For high rises, there is a big catchment. Sometimes they're very multi-story high, so definitely those catchments, the water hits the facade and then it just rolls down the facade, and you'll have a lot of water at the bottom of the facade. So yeah, definitely you have to consider it. And with ACCO, we can provide a performance solution for that. We've got our hydraulic programs that are based on steady, non-uniform flow that Rochelle touched on in her presentation. Based on that, we can discuss your site constraints. It might be the size of the drain. You might not be able to install something along the threshold that's very deep. Then we can look at how we size that up. We're going to size it up by, if it doesn't work with an outlet at the end, we can put an outlet in the center of the run. Otherwise, we can put multiple outlets on the run just to evacuate the water so it doesn't back up and into the building if it's definitely across a level threshold entry. So we can provide that documentation. We provide our proposals all documented using our hydro program, and we can provide the hydraulic plots so you can see visually how the drain is performing. As Anthony discussed in his presentation, blockage factors. We can apply blockage factors to our calculations also, and also take that into consideration when we are putting together the performance solution using our hydraulic programs. Definitely we can help the engineers with designing.
Thank you, Darren. This afternoon we've covered a lot. We've been talking about surface drainage in public spaces and building thresholds. I'd like to invite our speakers now, starting with Rochelle, then Anthony and Darren, just to leave you with their key takeouts from their presentations today. Rochelle.
The key takeouts would be that obviously we need to make sure we are draining away from our threshold towards our primary drainage element. We still need to consider accessibility, making sure our falls are correct, slip resistance as well. And just noting that we do have these tools available at ACCO where we can offer support across all of our representatives. We have our technical services team as well that's there to help you with any sizing queries you have. So takeaway is that there's plenty of resources available to support you on your projects.
Thank you. Anthony.
Thanks, Amanda. I think, my takeaways are fairly clear, and I think the most important one is that the design of the threshold in itself, not just the drainage, it is a coordination problem. It's the interface where drainage, accessibility, slip resistance, waterproofing, and maintenance must all be resolved together. And that's not just the responsibility of a civil engineer, but a lot of the time it does fall on their shoulders. A couple of other quick takeaways are the updates coming for most jurisdictions for NCC 2025. As a reminder, Part F1 now captures the drainage both of the surface and the subsurface together in one part, and Part F3 is rolled into Part F1. Appendix F of AS 3500 has gone from informative to normative, which is a big one. You must be designing your overflows at eave gutters with a supporting calculation. Number 4 is that valley gutter designs now have more flexibility, where before it was designed for a very small catchment, you can now design using a graphical method up to catchments of 400 square meters. Lastly, and this one is one that I was touching on with the question before, is make sure that you are designing for applicable blockage factors to AS 3500.3 with a minimum for your SAG pits of being 0.5 and 0.8 for other drains.
Thank you, Anthony. Darren, your key takeouts.
Yeah, look, I agree with both Rochelle and Anthony. Very great takeaways from your presentations. Very good. You can tell that Anthony's across all the changes in NCC and the Australian standards, and I've learned a bit today too on that. And Rochelle, all the level threshold design, what you need to consider, they're very key takeaways. So I just probably just want to round this up that with your designs, don't leave your specifications very vague and just label a level threshold is required at this. Detail, understand the application, and make sure you fully detail it, because what you want for you and your client is a long-lasting, durable solution. So a well-documented, specified detail of your level thresholds, including all the waterproof membrane, the correct type of product. Make sure it meets all the hydraulic performance and all the regulations, and then I think your asset owner and your client will be very happy with your design in the long term.
Thank you, Darren. And just before we do close today, just a reminder that we are running a competition, which you can enter by scanning the QR code on screen or use the link in the description box below. And just a reminder what the question is. The question is, if a certifier indicates that a level entry threshold to a large restaurant may require a performance solution instead of a deemed to satisfy approach, how would you approach your design? It is all the time we have for today, so please join me in thanking Rochelle, Anthony and Darren for their time and input. I'd also like to thank Engineers Australia's long-standing partner, ECHO, for their ongoing support. And as always, we're always looking at ways to improve and plan for future sessions. So if you could take a couple of minutes to complete a short feedback form, which is linked in the description box below. Please scan the QR code on screen to view and register for our upcoming events. Thank you once again for joining us, and I look forward to seeing you at our next Industry Partners event. Thank you and good afternoon.